Hi there. A while ago I looked at the power supply of the FY6600 function generator because it caused a massive stray voltage of almost 100 volts AC to be induced on the output terminals. If you are not familiar with it, I put a link to the video covering that investigation in the description below. As you can see, the function generator is happily running while I have its power supply out here in my hand. This video is about how I finally got rid of that power supply for good. If you recall, the original problem of the high AC was caused by the y-capacitor in the switch mode power supply, which couples the main primary side of the transformer to the low voltage secondary. The reason it is there is to suppress the switching noise, and since the FY6600 power cord has no earth connection, the designers used this method, which is used in practical all switch mode power supplies with 2-wire mains cables, like many laptop power bricks and USB chargers. The fix I suggested in that video was to replace the original 2-wire mains connector and lead with a 3-wire version that provides proper access to mains earth, remove the original y-capacitor, instead add 2 y-capacitors, one lead each soldered into the PCB where the original y-capacitor was, and connect the other ends together with mains earth. While this greatly reduces the stray voltage problem, it does not remove it completely, and sometimes the output's capacitive coupling to earth causes other problems in a test setup. The other problem I mentioned in that video is the heat buildup. The housing of the FY6600 has only very few narrow slots at the bottoms of each side and a couple in the rear panel. There's hardly any natural airflow, and if you keep the unit running for an hour, especially under load, you can feel the heat building up inside, which leads to drift in frequency and amplitude. For lowest noise and no stray voltages, I originally wanted to replace the switching power supply with a linear one, but these designs by nature produce a lot of waste heat and therefore not an easy solution for the FY6600. So I started to look into DC-DC converters instead. While looking for suitable components, I quickly realized there are tons of ready-made DC-DC converters out there, and so cheap that just buying the components would cost me more, never mind the time to build and test it. I decided to just buy some cheap converters from eBay and Banggood and test them for suitability. I figured at worst I could always use them to scavenge parts for a custom design if necessary. There is one big design decision you have to make, and this has to do with the fact that we need a positive and negative voltage. You can either look for a DC to DC converter that can do this, or stick with 3 ubiquitous converters for positive voltages only and create the appropriate isolated feed that allows you to basically tie the output of one converter to the new common ground and use that converter's ground as a negative output. This diagram shows what I mean. The 3 converters are all designed for positive outputs. By creating a completely isolated second feed from the AC transformer with its own rectifier and smoothing capacitor, the output of that converter can be connected to the others in reverse. Because its plus 12 volt is now tied to the common ground, the floating converter's ground becomes effectively the minus 12 volts with respect to the common ground. The drawback of this scheme is the considerable bulk, because we now need 2 rectifiers and 2 sets of big smoothing capacitors, and that is if you have a suitable transformer with 2 completely separate secondary windings of the right voltage and power. If not, you need 2 transformers requiring even more space, because we are talking proper isolated and bulky AC mains transformers here. As I managed to find a DC to DC converter that can do positive and negative voltage with reference to input ground, the circuit diagram and space requirements simplify considerably. Only one AC isolation transformer with a secondary voltage, rectifier and smoothing capacitor is needed to feed one conventional DC to DC converters for the 5 volts and the dual DC to DC converter for the plus minus 12 volts. With the space gained, I thought I might as well try adding a fan into the housing to solve the cooling problem. It would have to be one of the 40mm fans often used in 3D printers. However, I did not want to live with the noise of such a fan blowing at full speed at all time. Instead, the fan should have a variable speed determined by the temperature. The final diagram looks like this. The fan controller hangs off the plus 12 rail because unfortunately it isn't designed to survive the higher voltage of the DC behind the rectifier. The DC to DC converter can handle the additional current easily, but I was a little concerned about the noise added on the plus 12 volt line by the pulse width modulation of the speed control. For that reason I added an additional LC filter into the plus 12 connection to the main board. For the crucial plus minus 12 volt converter, I selected this module from eBay and tested each output separately with a 60 ohm resistor equivalent to a 200 milliampere load at 12 volts. It is supposed to handle more than 2 amps on each output, so the power requirement of the FY6600 will not cause any issues. The results of my measurements are here on the right, the top for the plus 12 volt and the lower one for the minus 12 volt. For each test I increased the input voltage from 5 to 30 volts in 1 volt steps, which is the x-axis. The blue line shows the output voltage against the left y-axis, and the red line shows the ripple in millivolts peak to peak against the right axis, and the green line shows the efficiency in percent also against the right axis. It is interesting to note that although an identical chip is used in both positive and negative sides, the positive is a poor buck converter and needs at least 15 volts input before the full 12 volt output is available. It is also slightly more efficient and less noisy than the negative side. The negative side works as a buck boost converter and produces minus 12 volt pretty much from the lowest possible input, which is for this chip 5.3 volts. The ripple curves are notoriously tricky to measure because the setup is sensitive to all kinds of stray noise from the environment, but it's still worth examining. On the plus 12 volt rail, there's a range from 15 volts onwards with relative constant ripple, while the buck converter is running properly and most efficiently. From something above 25 volts, the ripple voltage increases, and at 30 volts input it's almost double than the 15 volts ripple. On the minus 12 volt rail, we can see a distinct change in ripple when switching between boost to buck conversion at around 15 volts input. There are many choices for a single voltage DC to DC converter. I picked this one more or less randomly and tested it with 500 milliamp load as shown in the diagram. It's a buck converter, supposedly for 5 amp current, and while this seems to be optimistic for this tiny module, it won't have any issues with the load on the 5 volt rail for the FY6600. It needs only about 6 volts to produce the selected 5 volt output. There's a noticeable jump in ripple when going beyond the 18 volts input voltage. I suspect this is when the converter internally switches from continuous mode to discontinuous mode. Last not least, a quick view of the other two modules that ended in my shopping basket. This fan controller from eBay is simple but versatile enough to allow experimenting with different settings to find a compromise between cooling capability and fan noise. With the switch here, you can select to use either a fixed start temperature of 30 degrees or a variable one set by the trimmer resistor. Once the start temperature is reached, the fan starts moving slowly. If the temperature increases further, the speed increases linear until At 20 degrees above the start temperature, the fan runs at 100%. Since the fan controller uses pulse width modulation, it represents quite a spiky load on the plus 12 volt rail. To filter these out, I decided to run the plus 12 volts through an LC filter before it gets to the function generator. These are originally meant for use in drones to filter out the supply for the onboard video cameras. For some reason, it appears that all of these LC filters come with some additional polarity protection circuits underneath. I tested this filter, but only with the correct polarity, and I could not find any effect of the protection circuit. Hence, it can be ignored if you wire the filter correctly, which, with clear markings of V in and V out and plus and minus on the PCB, is not too difficult. These ready-made filters only work with positive voltages against ground, so as tempting as it might be for symmetry reasons, you can't add such a filter into the minus 12 volt line without reversing the capacitor and probably removing the protection circuit. If you instead implement the method with the 3 DC to DC converters and the 2 rectifiers I mentioned earlier, you could use these modules even in the quotes negative rail if you put it in right after the converter and connect the common ground at the output of the filter instead. Based on the measured performance graphs of the DC to DC converters, which I repeat here, we can see the expected performance depending on the DC input voltage range from the rectifier, which I indicate with the yellow band here. It's a band and not a line because the voltage will vary based on fluctuations of the mains voltage, which in the UK is normally 230 volts minus 6 plus 10%, so 216 to 253 volts. The other cause of variation is that AC output of especially smaller transformers changes by a couple of volts between idle and full load. This is caused by the significant internal resistance of the thin wire making up the windings. Taking these variations into account, the minimum DC voltage the rectifier must deliver is determined by the plus 12 volt buck converter needing at least 15 volts to work properly, while the maximum is determined by the lowest max input voltage of the converters, which is 32 volts. As you can see, finding the best solution isn't easy. On one hand, we need to stay well above the 15 volt limit for the 12 volt converter, even at low mains voltage, and with smoothing capacitor ripple taking into account. On the other hand, we would ideally like to stay well below 18 volts to avoid the increase in high frequency ripple from the plus 5 volt converter. From the 3 common transformer voltages, 15 volts works best in my opinion. A 12 volt transformer is just too low to work the plus 12 volt buck converter reliable, and 18 volts works fine, but with a more high frequency noise as a trade-off. What you see here is the inside view of the rear panel and the lid. Initially I planned to place the 40mm fan symmetrically in the middle of the rear panel. Obviously, I need to stay clear from the lower area where the USB and other connectors are. The upper limit is the ridge in the lid into which the rear panel slides when the lid is closed. In the end, I decided to move the fan more towards the power switch because this leaves more of the print of the rear panel intact, especially the pinout of the TTL out connector. This is the rear panel with the fan installed. For maximum airflow, I decided not to put any filters in, just a metal grill to protect my fingers when searching for the power switch. This is how the fan looks from the inside. Again, just the rear panel and the lid. It fits very nicely between the connector cutouts and the ridge in the lid. With the original power supply removed, I installed my scavenge transformer. Unfortunately, it doesn't have any mounting holes or brackets, so the only way was to epoxy it in. The transformer is quite heavy and bigger than it needs to be for the power consumed by the FY6600, but hey, that's what I had available. To make sure it stays in place, I decided to run 2 steel wires across the transformer and through holes in the bottom of the case. It's not very presentable, but it works fine for now. Anyway, you can see the remaining empty space in the housing for the rectifier, 2 converters, the fan controller and the LC filter. The best way I could come up with for mounting it all is this perf board, which on the left contains a fuse, rectifier, filter caps and the 2 big smoothing capacitors and PCB pin sockets, while I added matching pin connectors on the converters and the LC filter. One big problem with these eBay modules is that they often don't have provisions for mounting them. For example, the converter for the plus-minus 12 volts could accommodate at best 2mm screws, which also have to carry the electrical connections. Similar, there is no mounting provision for the LC filter. Soldering pin connections on each module and plugging them into sockets on the perf board seem to be the easiest solution. Because this raises all modules by about 10 mm, I needed to also raise the fan controller on a standoff that fits its single mounting hole. Otherwise, it would be very difficult to put the wires for the power and fan into its terminals. The row of 6 pins next to the smoothing cap is for the connector that came from the FY6600 main board and originally went to the switch mode power supply. Here's the underside of the perf board, which contains just a few point-to-point connections between the modules and the rectifier components. This is how the board looks with all modules populated. The loose black cable is the temperature sensor for the fan controller. The perf board fits snugly around the transformer and the space of the housing where the original power supply was. Note that I have removed all FY6600 boards for this view. This is a side view with everything installed and powered up for a test. The temperature sensor is just loosely wedged into the heatsink of the FY6600. The 2 LEDs on the dual converter board show that the converter is producing a positive and negative output voltage. This is a view from the rear panel. Here you can see that the original connector from the FY6600 simply plugs into the 6-pin header on the perf board. I should point out that while this works absolutely fine, there is now of course no guard that would prevent you from plugging in this connector the wrong way. I can tell you from experience that you can easily shift the FY6600 connector by 1 pin, which shorts both the plus 5 volts and plus 12 volt rails to ground. And that's exactly what the 1.6 amp fuse in the AC line from the secondary is for. After correcting the wrongly positioned connector and replacing the fuse, everything still works. The last thing to mount is the temperature sensor. Where to put it? Initially I had it slightly wedged into the heatsink on the FY6600, and the effect is that after about 5 minutes from cold, the fan starts running at slow speed and so silently that it's just barely noticeable, and then only if nothing else in the room was making any noise. When the lid is closed, it's actually easier to feel for the airflow than to listen to find out if the fan was running or not. So in the end I decided to leave it where it was, but connect the sensor more solidly to the heatsink by simply putting a long screw to one of the fins with washers on both sides. This gives the sensor a reasonable mechanical and thermal contact that can be easily undone, and I did not have to modify or remove the heatsink in any way. Initially I had planned to block the remaining 4 rear vents next to the fan because I thought leaving these open would lead to some sort of airflow shortcut, that is the fan extracting the air that it just sucked in from the vent next to it and nothing from further inside coming through the vents on the bottom left and right. Before doing it, I decided to run a test to see the effect. I used sticky tape to fix the temperature probe to the top of the enclosure and then record the temperatures in the enclosure in 10-second intervals. As you can see on the graph, when the fan starts kicking in, the initial steep rise of the temperature curve flattens considerably. After about 1.5 hours, when the temperature had reached a steady state, I used a piece of tape to cover the rear vents from the outside and kept everything running for another 1.5 hours before turning the power off but keeping the recording of the temperature on for a while longer. It is clear that blocking the vents is not a good idea because the temperature jumped up by 2 degrees. I suspect that the fan's suction causes air to enter the vents and swirl at a much larger curve than expected through the entire enclosure before being exited back out on the fan. It is interesting to note the bump in the temperature after the power has been turned off on the rear. This means the fan stops and the residual heat is enough to drive the temperature up by almost 2 degrees before the unit slowly cools down. You can avoid this heat build-up if you turn the unit off in 2 steps. First, press the power button on the front, which just puts the generator in some kind of standby mode but leaves the power supply and fan going. Then, after a few minutes, turn the power off at the back too. So I spent about £20 on the modules and the fan. Is that cheaper than building your own DC-DC converters? It is hard to say because some parts are difficult to get in one-off quantities, and how do you rate all the extra stuff you have to buy and then ends up in your spare parts bin? It certainly shifts some of the work from pure electronics to mechanical, like how to mount and wire up things instead. I reused an existing transformer. If I had to buy one, I would consider getting an external one. They look just like ordinary wall chargers but produce AC instead of DC. Just make sure it's a properly rated isolation transformer. This would save a lot of space and mounting headache and lowers the temperature inside the unit even further. In my tests, I looked specifically for any issues affecting signal quality, but as far as I can tell, there's no difference to using the original power supply. Thanks for watching.